Okay, so I'm going to do number 44 with you guys. Number 44 says that y is supposed to be equal to x squared plus 2x minus 6. Before I even graph this thing, I actually know one thing right off the bat. I know the y-intercept.
It's negative.
It is. It's negative 6. The constant term, the last number, if it's written in this sort of format, is the y-intercept. So that helps right off the bat. My expectations, well, I guess let's start by just graphing it. X squared plus 2x minus 6. I think just a window that goes from negative 10 to 10 is probably sufficient. Yeah, that'll work. So one of my expectations is just make sure you tell me what your window size is. So your window size should go from negative 10 to positive 10, although you can change it if you want. I don't actually care. And I'm going negative 10 to positive 10 right here. Start with that. Graph me like roughly where it's at. So it looks like this one looks, I don't know. There. That's about what it looks like. I don't think I talked about this last day. Standard convention would be to draw arrows, by the way. Arrows just implies that the graph keeps going. I mean, this picture of the graph makes them stop, sure, but the graph does continue in both directions. Everybody okay with up to this step? Okay, last part. We need to calculate any really key values. So the main ones I'm expecting from you guys would be the x-intercepts, the y-intercepts, the minimum or maximum value, and can I throw a couple more on the list as well? You guys should also write down the domain and range. So let's start with the y-intercept. I already know what it should be. It should be 0 and negative 6, but let's just prove that. Anybody remember how to confirm that in your calculator? What one of the ways would be? Yeah, go second calculate the value when x is 0. Or, second way, go into your table and 0 is at negative 6. Okay, so there's one. We'd also like to find these x-intercepts. It looks like there's 2 of them, which makes sense because quadratics can have up to 2 answers, or 1 answer, or there is no answer is an answer. So, as I scroll through the table, though, I don't see y ever equaling 0, though. So I need to use a different method. I have to go second calculate a 0, number 2 here. And this is the function where you have to put the cursor on both sides of where the 0 happens to be. So I'm going to find the one over here that's positive 1 point something maybe. I got, let's go with 1.65. 1.65 and 0? Did you get that too?
I haven't done that one.
Oh, did you do the other one?
Yeah.
What did you get for the other one? Let's just save time here.
Negative 3.64.
Okay. Sounds like at least you guys were saying out loud you kind of know how to solve for these. Anyone have any issues that I can help troubleshoot right now? You know how to find those numbers? Okay. The last one on here that I need you to find is the vertex right down here at the very, very base of the graph. It looks like it's right next to that 0, 6. So we go second calculate the minimum, because this is the lowest part of the graph, so minimum part of the graph. And then same thing, you just got to go on the left and right hand side. So once you know how to use your calculator, man, you can do anything. So okay, here's where you have to be a little smarter than your calculator, because yours might say something different than mine. This says negative 0.9999999 repeating. What does yours say? Anybody else calculate that one?
I got negative 0.99.
Okay.
I got negative 1. I got negative 1.
Yeah, we should just call it negative 1. This is just the way that your calculator regresses in calculus to try to calculate that value. So call it negative 1 and negative 7. Don't say 0.999 repeating. That's kind of silly.
I put 1.0. Does that make it different?
No, 1.0 is fine. Okay. Wrong. Okay. 2 more things then. Can we add to our list of things that you do? Can you always write down the domain and range as well? So you can just put this off to the side. The domain and range. Domain so far is actually very boring. We will get to domains that are more restrictive. Domain means what x value can you plug in? And you can plug in anything you want. There's really no restrictions here. So we write it like this. X is an element of the reals. Could you plug in 5 for x? Sure. Could you plug in 1,000,000? Okay, I don't know why you would, but you could. Could you plug in -17? Sure. The range, though, is a bit more restrictive. The range is what sort of y values we have. Could y be +5? I think so. Way up here, I think you get 2 answers even. Could y be -10 though?
No.
That doesn't go that low. How low does it get to? Well, actually, it looks like it gets to -7 here, right? So you're going to say y is greater than or equal to -7. That's the lowest point this graph happens to get down to. If you like my vending machine analogy, you can put any amount of money in the vending machine you want. You can put in $1, you can put in $2, you can put in $1.39728, you can put in $1 billion. But there are certain numbers that you can't get back. You could get back a 1 or a 2 or a 3. You could even get back -1, -2, -3, all the way to -7. But -8, not possible. It's not in the vending machine. So you can't get the number out of the vending machine. Sure, that's a good example. Yeah. Okay, any issues with that? Feeling comfortable there? Okay, so my goal today then, with the notes we have, we're going to do some expanding on this. You guys have already learned about linear things. Linear things are in straight lines. And they always fit the pattern y equals x to the power of 1. We've also done quadratics at some point. Quadratics look like this. And those will fit the pattern y equals x to the power of 2. Well, today we're going to learn x to the power of 3, x to the power of 4, x to the power of 5, x to the power of 6. And you're expected to be able to understand how to graph these things to at least the power of 5 or 6. But truthfully, once you get how the pattern works, I could ask you to graph something to the power of 17. And you should probably be able to figure it out, because you got a graphing calculator. By the way, I threw rationals on here as well. We didn't ever actually graph rationals, I don't think. But we could do rationals. Do you guys remember what rationals are? Like fractions, basically. Is that what you said? Yeah, like we could do the graphs of fractions like x plus 1 over x, but we don't typically, like, you're not actually required to know that in Dash 2 curriculum. In Dash 1 curriculum we did this, but we don't actually graph rationals. So I stole this out of my 30-1 notes. So if you guys want to put a note here, we don't actually graph rationals in Dash 2, but we could, but we don't actually, we're not required to. So they're much more harder. Much more harder. Yep. Much more harder. Okay. Okay, quick note here. Polynomials, linears and quadratics are considered polynomials. We're just now going to add to the list. So let's do some examples. Not that one. Linear is like x to the power of 1. Quadratic, x to the power of 2. So in case you're wondering what the terminology is, cubic is x to the power of 3. Quartic is x to the power of 4. And if we ever get that high, I think 5 is quintic. Okay. What would this top one here be? Good. Yeah, that's cubic. This one right here we would not ask you to do. This would be multivariable because there's m's and n's. And you know how we talked about function notation the other day? This would be f of x equals this. This would be f of a equals this one because a is our variable. But I couldn't do that on this next one here because it would have to be f of just a single letter. And I can't have 2 letters, at least not in this sort of math course. So I'd never actually ask you to graph this one right here. This one right here would work. This one's linear. And I should point out, this is actually still considered polynomial. The reason why is that you have 0 x to the 5s. You have 0 x to the 4s. You have 0 x to the 3s. And then you finally have a constant term. So even though it doesn't look like it's a polynomial because there's not more than one number there, technically there is. We're just skipping writing all of the zeros. That make sense? So this is actually known as a constant function, which isn't on my list. A constant function actually has no x's in it at all. Hence, it's a constant term. So, here's just a slide just reviewing some of the terminology we're going to use in the course of this section here. The last term that has no x is known as a constant term. By the way, your constant term, your y-intercept. Your linear term then would be if you have any x's in it. The leading coefficient is the very, very first coefficient. And it kind of affects the direction of the graph. In a linear graph, it controls the slope. The slope could either be uphill or downhill. And it does similar things as we learn about these new graphs. The other thing I need you to know is the degree. The degree is the largest exponent. So if it goes to the power of 2, the degree is 2. If it goes to the power of 5, the degree is 5. Okay, so let's start by drawing these graphs. Are these polynomial functions? Yeah, I know it seems dumb to write it like this, but really you have 3 x to the zeros, because you have 3 of things that have no x's. You have 0 x to the 1s. You have 0 x to the 2. Now, we'd never write all of that, but this technically is a polynomial. So we're going to graph it. So y equals 3. What's the graph look like? Flat across. Let me give you the vending machine analogy again. If you input 1, it gives you back 3. You input 2, it gives you back 3. You input 17 billion, it gives you back 3. Does that make sense? The rule in this case basically here is, I don't care what you input. It's really irrelevant what x is because there is no x in this equation. Regardless of whatever x is, y has to be 3. So your graph, if I did a quick little sketch here from like say -10 to 10.
Please excuse the interruption. Junior high teachers, the students from the Horse Whisperer program have returned.
Horse Whisperer.
Please don't allow them in without a late slip.
How come I remember about horse whispering?
Horse Whisperer.
Horse whispering.
Cool. All right. Anyways, this is what your graph would look like. Just basically, it's a line straight flat across. Let's talk about some of its properties then. Does it have an x-intercept? No. It does have a y-intercept, so I should expect you to label that. But, I mean, everywhere on the graph literally is the number 3. So this would be at 0 and 3. There's really no like maximums or minimums we need to worry about, so this would suffice for the graph. I do want to ask you, though, about domain and range. What x number could you type in? Sure. If I plug in 0, I get 3. If I plug in 1, I get 3. If I plug in 2, I get 3. Is there any number that I could not try to plug in? No. For right now, by the way, we really don't have much for restrictions. So x is element to the rails. What about the range, though?
Yes, 3.
Yeah, literally, it's not even above or below a number. The range is that y has to be 3. It's not above 3, it's not below 3, it's just 3 and only 3. I don't know that I need to do the second example, because honestly it's the same, right? -7.4 is just going to be a line flat across out at -7.4. I do want to talk about this function, though. This is known as a constant function. Does anybody know what the degree of this function is?
1.
Not 1.
Oh, 0.
The degree is 0. And the reason why the degree is 0 is because what is the biggest power of x we have? Well, the answer is we don't have an x. Therefore, we have 0 x's. So therefore, the degree is 0. Does that make sense? So if the degree is ever 0, flat line across. So far, so good? Cool. Fine. So that's what I have on this next slide here. Your constant function is basically flat line straight across. Your domain, well, you can use anything you want for x, but your y value is just c. I'm going to elaborate on this term a little bit later, but this would be known as an even degree, because the degree for this one, we just said, was 0, and 0 is an even number. I'm going to come back to even versus odd later, if that's okay. but it's even. There are no x-intercepts. There can't be. Does it cross this line? No. There's one exception, though, unless everything's an x-intercept. What graph would that be? Where everything was an x-intercept. If it was right on the x-axis, so you're right, which is 0, yeah. If you had the line y equals 0 straight across this, I guess in that case, literally everything would be an x-intercept. It's kind of weird. So, okay, let's try the next example. Let's try these ones. What sort of functions are these? Yeah, we call them linear because the power is 1 for these ones. These are linear. The degree is 1. So when I talk about even and odd a little more in a bit here, these would be considered odd functions. So let's graph them. So the first one is negative x plus 1. Negative 10 to 10, negative 10 to 10, and the graph looks roughly like that. Okay, key points. Which one? What sort of key points do we have to look for here? X and Y intercepts, it looks like. So, hopefully by now you're fairly fluent in your calculator. You know how to do that. So if you're not, let's do it again. Second calculate the value when x equals 0. That'll tell you that your y-intercept's at 0 and 1. And if you second calculate the 0 function and do the whole, like, both sides of the thing, it's actually at 1 and 0. So are you okay being able to calculate those? Are those on your own? Okay, one last thing. Add this to your list. Get in the habit of doing this. Let's find the domain and range. So at first, the domain, honestly, is very boring. For polynomial functions, it's always everything. Could you plug in x is 5? Sure. 6? Sure. 7? Why not? I promise you, we will eventually get to a point where there are certain numbers you can't use. But for right now, you can plug in anything you want for x. That's not a problem. What about your range? Yeah, it looks like as I'm looking at this graph, I should be able to get a y value back for anything because the graph kind of extends from top to bottom, right? Does that make sense? So because it extends from top to bottom, I could find a y value for anything I wanted to. I should be able to. There's no value where it's like too low for it.
David and today a good striker, please come to the office.
Like for example, if I wanted y to be 7, yeah, look, that's where y would be 7. If I wanted to be y be a 7 million, well, 7 million is way up there, but I'm sure that up here at 7 million, it will eventually cross, right? Does that make sense? Okay, let's talk about the leading coefficient. What's the leading coefficient in this graph? It's -1, yeah. And what a negative does to the graph is it causes the slope to go downhill. Hopefully you've seen that at some point before. I don't really need to graph this next one to know something about it. Because of this 2, the graph should go uphill probably, right? The +1 is your y-intercept. Yeah, that's what I calculated. So let's do some notes on this one then. Linear functions, usually write them in the form y equals mx plus b. Or we might write it like this. This is a little more complicated, but it would be ax to the 1, bx to the 0. So you have a certain number of x's, and then you have a certain number of numbers that don't have an x. Let me say that one more time. You have a number, then you have x, then you have a number, and then you don't get to have x. X to the 0 basically means you don't need it. So the domain of these things is always x is an element of the reals, but so is the range. You should always have x's and y's all the way throughout the whole system. It's known as an odd equation, so we'll come back to that. There should be one x and one y intercept. Now they might be through the same spot, but you should have one of each. Right? Like as I draw a linear line through this thing right here, yeah, look, there's one of each. There's one of each. So you should have one of each. And the graph extends with the same slope over the whole domain. Still doing good? Cool. Okay, next one. Well, now we've got some things that are quadratic. How do I know these are quadratic? There's an x squared, right? So let's speed this up a little bit in case you're getting a little bored with this, because this is really the review section. So why don't we just do this one right here? Just because that one's maybe the most interesting. There is -1 x squared. There's a +9. How many x's are there? There are 0 x's. Does that make sense? There's -1 of your x squared. There's no x to the 1s. And then there are actually 9 x to the 0's. If I actually wanted to write this out kind of in a longhand way, that's how you'd write it. But I mean, we wouldn't do that on a calculator. That's kind of silly. So, what is that negative sign going to do to the graph, though?
Flip it upside down.
Yeah, it flips it upside down if you've seen quadratics before. -x squared plus 9 should cause a quadratic. Well, that barely fits, but that'll work. Causes a quadratic that goes upside down. Why is it upside down rather than right side up? Because that negative sign, that's what it accomplishes. This +9 is your constant term. I'm fairly confident without even trying it that my y-intercept right here then should be 0 and 9. But I mean, what the heck? Let's just test it. It takes 30 seconds. Yeah, Cole. Oh, give me a sec. I'll come help troubleshoot. But look, I just proved 0 and 9 is your y-intercept. Well, if you go from 10 to positive 10, you got to go from -10 to 10, and then from -10 to 10.
What?
Still doesn't work? You guys are the different ones. Okay. I'm fairly certain that 0 and 9 is actually the maximum point on the graph too, isn't it? Because if you solve it for the maximum point, I think that's as high as it gets. So the only other things I need to do here, I should label my axes as -10, 10, -10, 10. Has anybody calculated these x-intercepts yet?
One is -3, 0.
Okay, -3, 0.
And then the other one is 3 and 0.
Doesn't that kind of make sense that it's probably one's positive, one's negative? Like they should be kind of equal distance from each other? Any issues with that so far? Okay, let's talk domain range then. Domain's really boring. It is anything you want it to be. You can plug in x as 5 billion if you want, or -3. Range is a bit more challenging. Anyone want to take a stab at the range?
Y has to be less than or greater than 9.
Less than or equal to 9.
Yeah.
Yeah, make sure you write the symbol the right way. Y has to be on the smaller side of 9. If you wrote this, y is greater than 9, that's very much incorrect. Like, you're on the wrong side. So far, so good? Okay. Well, let's do this set of notes on it then. Quadratics usually get written in one of two formats. If you were in -1 last year, you might recognize this format right here. This was called vertex form, because it indicates to you where the vertex of your graph is. We don't actually worry about that in 30-2, so if that was not your favorite thing last year, don't worry. This is just one of my 30-1 slides, so most of the time we write it like this. You have a certain number of x squareds, you have a certain number of x's, and then you have a term that has no x's, a constant term. In the example we just did there, we didn't have a middle term because there were 0 of them, that's all. Okay. The domain, well, again, it's anything. Here, the range is either less than or greater than a certain number. If you know how this vertex form works, Q is like this point right here. Like on this one here, it was 0. On the one you guys just did, it was 9, I think, right? 9 is as high as the graph got. So it's either greater than or less than 9. You just got to figure out which sign to use. What is the degree of this graph? 2, yeah. Well, 2 is an even number. So give me one more minute, then we'll actually talk about even versus odd, figure out the pattern. This thing could have 0, 1, or 2 x-intercepts. Let me show you some examples of this. Here's a graph that has no x-intercepts. Here's a graph that has just 1 x-intercept. And here's a graph that has 2 x-intercepts. This kind of fits with that whole quadratic formula. There could be one answer, there could be 2 answers, or there could be no answer, right? So, okay, here's something really important. The graph will start and end in the same quadrant. I need to change that word because it's really not quadrant. Do you guys know how the quadrants of the graph work, where there's like 1, 2, 3, and 4? You guys know those quadrants? I actually did this wrong. I shouldn't say in the same quadrant. Can we change that to the word hemisphere? And by that I mean, if the graph starts up top, it's going to have to turn around and end up at the top again. Does that make sense? And let's say the graph starts down here at the bottom. If it starts at the bottom, it's going to end at the bottom again. How does that compare to this last one right here? Does it start and end in the same hemisphere?
No.
No, it goes across the graph. And now's a good time to talk about even and odd. Okay. Even functions will start and end in the same hemisphere. This is a pattern we'll discover in a bit. But odd functions, they'll go like across the grid. So here's a linear function. See how it goes across the grid? Here's a quadratic. Starts and ends on the same top or bottom of the graph. What was the very first function we talked about? Yeah. It's even. Does it start and end in the same hemisphere? Yeah. This one starts up here at the top. This one ends up here at the top, I guess. Does that make sense? It doesn't go across the graph like that. It's actually a pattern that will be useful when we try to figure out the new functions that we have next to cover. So, how am I doing so far? Is that mostly a review? Okay, take 5 minutes. Because then after that, now we're going to build on the new ones. The cubics, the quartics, and the quintics. So, take a 5-minute break though. Keep going here. Okay, so here's the new stuff then. Now I want to show you how to the power of 3, 4, 5, and 6 work. And what you'll discover is that it's actually very similar once you pick up on the patterns behind them. So let's try graphing, let's just the first one, I guess, the 5x to the 3 one. So to graph this one, it's going to be 5x. And if you don't know how to do it to the power of 3, you may have to do the little up arrow that's above the divide by sign to the power of 3. My calculator is one of the old ones where it actually will put the little, I don't know, up arrow thing there. But some of the new ones, it'll actually make it go like up as a top script one and make the 3 go up there. Just make sure you come back down again before you type the plus x to the power of 2 minus 4x plus 1. Good so far? Okay, let's try graphing it. For the most part, this graph, actually, I seem to see most of the important stuff on this graph. But we may occasionally need to change our window size so that we can see all of the key points. But hopefully you have this. Do you have that? You gave me a funny look. You do have that. Okay. So let's graph this thing. From negative 10 up to positive 10. Negative 10 over to positive 10. It looks roughly like this. It goes up a ways. Then it has like a little flip. And then it goes back up again. That's about the gist of what this graph looks like. So I'd like to talk about a few properties of this graph I need you to know about. The first one is the direction of the graph. What is our leading coefficient? 5. 5 is a positive number. by virtue of it being a positive number, this graph, although it has like a little flippy twist in the middle of it, it's kind of like a linear graph in that it's going uphill almost the whole way. Does that make sense? Ignore that little flip, that little S curve in the middle there. Essentially, it's like a linear graph in which it's odd. So by virtue of it being odd, it's going to go all the way across the quadrants. And it's positive, so it goes uphill. If we had a negative leading coefficient, it would have more of a downward trajectory to it. So that kind of fits. Let's try to calculate some of the key points I'd ask you to solve for. Drawer. Anybody found any of these points yet already?
Well, the y-intercept is 0 and 1.
Yeah, we know that. How'd you figure that out, though?
From the formula.
Yeah, the constant term. There's a 1 back there. So it probably is at 1. It looks to me like we only have 2 intercepts. There's an intercept way over here. And I think this guy right here just barely touches, I think. So let's try solving those. Second, calculate the 0. Okay, so I got one of these at negative 1.09.
Yeah, that's what I got too.
Okay, that's good to hear.
0.6.
You got the other one already?
I got 0.6.
For this one right here?
Yeah.
Okay, well, I'll try it too then, I guess. Second, calculate
Yeah.
the 0. Now, we may actually want to zoom into that area there and see whether it crosses once or twice. Because I just got 0.3. What did you get?
4.6.
Okay, so based on that, we need to take a closer look. Because I'm thinking what happens is there's actually not just one intercept in there. There's like this line, and it's just going barely over and then back again. So we need to zoom in a little bit.
Oh, it does.
So if you've seen this, go zoom in, if that makes sense. And then the way zoom in works is the cursor is somewhere on the map here. You need to take the cursor and put it in the general vicinity of where you want to zoom. Press enter.
Where do you zoom?
Well, we want to zoom a little bit closer so that you get. Can you see now a little bit better here? The graph actually just barely goes over and under. So there actually are 3 intercepts here.
What?
Does that make sense? So I actually should write like 2 different dots here. One of them, what did you say, was at 0.3?
Yeah. 0.3, 0.6.
And then the other one looks like it's at 0.6. So there's actually 2 of them in there. So that's an important skill to have. You may need to zoom really close to the axis once in a while and see whether it just barely touches once or where it actually like goes over and gives you 2 intercepts. Because if we weren't really careful there, you got 0.3 probably because your cursor was closer to the 3 side, and you got 0.6 because your cursor was closer to the 6 side. So there's actually a few other points that you might get asked to solve for, but this graph is getting kind of busy right now. But I could ask you to find, I'll label them with a new color here. You could get asked to find this maximum value right here, because it's kind of like a half a quadratic. Now, let's not bother with it today, though, because this graph is busy enough as it is. But there is a bit of a maximum right here, and there's also a bit of a minimum somewhere in there, where this graph has a little low spot right there. We could find those as well if we needed to, but I feel like you guys know how, so we'll move past this. So let's talk domain and range. Well, as it is for the first couple of days, domain's everything. What about your range? It is everything, yeah. Because essentially this graph, it starts way down here in the deep negatives, and it finishes up here in the high positives. Every single y value is at least accounted for at least once. So let's talk through the notes on this. This is a cubic function. The way that cubics work is you need to have an ax to the 3. There's a typo here. You need to have something to the power of 3, then to the power of 2, then to the power of 1, then a constant term. But the domain and range is always right across. So you can have pretty much every value you want there. And that's because it's an odd degree. Odd degree things always go diagonally across the map. Now they could go like this across the map. They could go like that across the map too. How would I get something to go this way? What would that require? Good, a negative leading coefficient. Yeah, there you go. Okay. Now the way that cubics work is usually there's a little bit of a flip in the middle. They're not straight anymore. So the two most common kinds of cubics would look like this, where it actually has a full twist, like that. Or like the one I have right here, where it doesn't do a full twist, but it just kind of does like a little flattening out section, and then keeps going again. Those are kind of the two most common types of cubics, where you may actually get a maximum and a minimum right here. Or maybe it just kind of does a little flippy section in the middle. I don't have a better word for it than that, so I call it the little flippy section. Yeah, something like that. So based on that, though, you could have 1, 2, or 3 x-intercepts. Let me show you how that might look. If you wanted to have 1 x-intercept, it could look like this. That's a cubic. It has your little flippy section right here, but it only crosses once. That's 1 x-intercept. It could have 2 x-intercepts. To have 2 x-intercepts, it would look something like this. It would go up, it would come back down, and it would just barely touch. Like for us, ours went kind of underneath the bottom there a little bit. But if it just barely touched the axis, you could have 2 x-intercepts. Or, if it has the right sort of flippy section in the middle, it could do like that. It has like a bit of an S-curve into it. And it could have 3 x-intercepts. Could it have 0 intercepts? Why not?
Why not?
Yeah, why couldn't it have 0 intercepts? And what do odd functions do? They go across the map. Yeah, since they have to go across the map, it has to cross at least once, right? So I guarantee you have to have at least 1 x-intercept here. But it could be 1, 2, or 3. Well, it can't have more than 3 because to do that, it would have to flip back around again. And that's going to happen on the next odd one. So you know how we're talking about to the power of 3? Well, let's zoom ahead a little bit here. If it was to the power of 5, the power of 5 has 2 flippy sections, where you have this little right here, and then it gets a second one. So there could be 1, 2, 3, 4, 5, but it would have to be the power of 5 for that to occur. Does that make sense? If a graph had, like, say, that, I could probably guess what the power is. 1 flippy section would make it to the power of 3, a second one to the power of 5, to the power of 7, to the power of 9. This is probably an x to the power of 9 graph then, just based on how many little flippy sections it has. I'm dead serious. I have no good word for that, by the way. Like, I do not know what it is. So, does that make sense, though?
Yeah.
Cool. Okay. What else was I there? Yeah, I guess let's look at this slide here. So, start looking at some of the patterns we recognize here. Linears go across the map. Cubics go across the map. On the next slide after this, no. Here it is. Can you guys find this slide? Sorry, I know it's a little bit further ahead here. This is a degree 4. This would be what an x to the power of 4 looks like. And do you see how it looks kind of like a quadratic? Only it's a quadratic with a flippy section. This one right here is a degree 6 because it's kind of like a quadratic, only it's got 1, 2 flippy sections. Does that make sense? So every time it does an extra little one of those things, it usually means it's another degree. Now the flippy section could look like this. It could be like very distinct. Like that W shape means it's probably to the power of 4. Because if it looked just like this, it would be quadratic. So having it fully turn around means it's probably the power of 4. But it could look like this. It could look like this, and then do like a bit of a turn like that. Do you see how it still kind of got like a little bit of a flippy section, but it didn't actually turn all the way around again? That still counts. So kind of like with your cubics where it could do this, or it could just kind of flatten out and keep going. Both of these would be the power of 4 type graphs. The reason I know that is because they start and end in the same hemisphere. If they start and end down here, or start and end up here, they're in the same hemisphere. Does that make sense? Scroll back. I skipped a few slides here. Let's look at the ones I missed here. So, what's unique about this cubic right here that I drew? Why is it backwards? So how do you make it go downhill, though? Good, yeah. And then the same thing with this one. This quadratic is facing downwards because there's a negative leading coefficient. But this linear one that's going straight up again must have a positive leading coefficient. Does that make sense? So I would expect this one to be like a negative x squared. This one would be a negative x to the third. But this would be a positive x because it's going up rather than down. That's all. Here's a slide just showing what I think I showed you earlier, the idea of how you can have 1, 2, or 3 different roots. So, okay, we just looked at this slide here. Let's look at this one then. Tell me something about this graph right here. What power do you think it probably goes to? The answer's 4, yeah. It looks kind of like a quadratic, right? Where it starts and ends at the top. So it looks roughly like a quadratic. But it has the little flippy section in the middle. So it means it's most likely an x to the power of 4 with a positive leading coefficient. Does that make sense? Now, I don't know what the x to the 3 or the x to the 2 or the x to the 1 happens to be. But I do know one more thing. I know what the y-intercept is. It looks like there's probably like a plus 30 as my last term. So that's about what I can tell you about this graph right here. I know that there's a positive leading coefficient. I know it's an x to the 4. I don't know how many x to the 2s or x to the 3s. So it could be plus 7x to the 3 minus 4x to the 2. We don't know about that information. But I do know the last number is probably about 30 because it's about 30. Does that make sense? Do the same thing here. Tell me what we know about this equation. Okay, so degree of 3 it looks like, right? Because it looks like it kind of has the flip around. By the way, another good giveaway, if it has 3 roots, it's probably to the degree of 3. If it has 4 roots, that's a good idea, that's to the power of 4, right? So probably an x to the 3. Positive or negative for it? Yeah, why? Because it's kind of going downhill, right? Now, I don't know how many x to the 2s it has or how many x to the 1s it has, but we should be able to tell you what the constant term roughly is. 6. Yeah, I'd say 6. Right? If that's 5, that's probably 6 right there. So it could be 7x squared, it could be 9x to the 1. I have no idea about these numbers. Like, these ones here are we don't know them for sure, but we should know the rough idea behind them. What I need for you guys to be able to do then is 2 things. If you're given an equation of a graph, I need you to be able to graph it, which is more or less what we've been doing so far. If I give you an equation, I should be able to say graph it, tell me about the graph. But the other thing I need you to be able to do, and this is very common on the diploma, they're going to give you a picture of the graph, and I'm going to ask you, what are some of the properties of the graph? So that's like what we just did here. One of the properties of the graph is that this is an odd graph. Another property of this graph is that it has a degree of 3. Another property of this graph is that it has 3 roots. Another property of this graph is that it goes across the grid as opposed to starting and ending on the same sides. Does that make sense? So you just need to be able to recognize those.
So is end behavior like...
Yeah, when they talk about end behavior sometimes, that is like, does it start and end on opposite sides? Or does it start and end on the same sides? You ever hear that phrase? They like to, on the diploma, do something like this. They make like a grid where they'd say, give me a second, let me make a question for you. 1 would be even. 2 would be odd. 3 would be 1 root. 4 would be 2 roots. 5 would be 3 roots. 6 would be no roots. 7 would be positive leading coefficient. 8 would be negative leading coefficient. Okay, so here's what they might do. They might give you a whole list of properties. And then it's numeric response. They might give you a picture of a graph, Or they might just give you an equation and they say, which of these properties fits this equation? So like, for example, this graph we just did right up here. If I were to ask you, like, which properties fit, is it even or odd? You'd say it was odd, so you'd pick 2. Were there 1 root, 2 root, 3 roots, or no roots? This one had 3 roots. That's a 5. Did it have a positive or a negative leading coefficient? Does that make sense? And so they might give you a whole list of properties and then say which properties fit the graph. Right, cool. Okay, this slide right here just reminds you that you still have that graphing calculator. So you should be comfortable using value, 0, min, max, and intersect to try to find some of those key points. One more thought though. It is possible that they might require you to use the quadratic formula or factoring still. And the reason I say that is that the quadratic formula is on your data sheet. They wouldn't put the quadratic formula on your data sheet unless there's a chance they might ask you to use it. So let me give you an example of where that might come up. Let's say that they told you the equation was x squared plus 5x minus 2, and you had to find where it equaled 7. One of the ways you could do this would be to graph the equation, plug number 7 on there, and see where they cross. Does that make sense? That would work. But if they gave you the right sort of question, they might ask you to use the quadratic formula instead. How would you use the quadratic formula to solve this question? Do you guys remember? Okay, pull the 7 onto the other side, so you'd have x squared plus 5x minus 9 equals 0. So it'd be negative 5 plus or minus the square root of 5 squared minus 4, 1, negative 9, all over 2 times 1. So I just want to remind you of this. They throw the quadratic formula on your data sheet. As a teacher, I take that as it could happen. It might not. Technically, the quadratic formula is not grade 12 curriculum. No, it's grade 11 curriculum. Like both 20-1 and 20-2 is where the quadratic formula lies. That being said, I've seen this before on the Math 30-1 diploma. Every year for the last couple of years, they've been putting a quadratic formula question on there, which is frustrating because it's not technically 30-1 curriculum, it's 20-1. But so anyways, I feel like it's responsible of me to remind you that you should still know how to use that. So when can you use the quadratic formula? Only if it's a quadratic. Okay, so if it's not quadratic, don't worry about it. But it's possible they could ask you that. Okay, we probably don't need to do all of these graphs, I'm thinking. So why don't we just do the last one? Do C. Here's a graph. What I'd like for you guys to do, graph this thing for me, and then tell me all of the properties you can think of. So, I mean, you should find me x-intercepts, y-intercepts, domain, range. Tell me about the end behavior. Tell me what the degree is. Basically, graph this thing and tell me everything you can about it. So, I'll give you guys a head start to try it first. So here's the first issue you guys are coming across here. I don't think I've actually had one of these yet. When you graph it, does it show up nicely on your grid? No. You may have to mess around with your window settings. So negative x squared plus 13x plus 12. So currently my graph makes it look like this. That's all I got actually.
Yeah, that was me too.
If I go to a zoom standard at 10 by 10,
Oh, I did 100.
10 by 10 isn't really enough. So here's where we have to use some of our knowledge of what this graph is going to look like to help us out. There's a negative leading coefficient. What does that mean? Okay, so it means it's upside down. And based on the way this looks, I feel like it's going up right now, and then somewhere in the future it's going to come back down again. So here's what I'd do. We need to affect the x values. We need to make it go further than 10. So I'm going to make it go to...
100.
Well, I'm going to try 30 first. We'll see.
It doesn't work.
30 was enough.
What? Oh.
Like, okay, so in the window, I said the x value. I made the x value go to 30. Are you guys talking about the y value though?
Yeah.
Because the y value means that the graph is way up there, right? How high did you guys make the y value go up to? 100?
I went to 240.
Was 240 enough?
80.
80 for the y value?
Yeah.
Okay. There you go. Okay. Now your graph is going to look different than mine, but here's how mine would need to work. I would need to draw a bit of an axis that looks like this.
Oh, that looks way better.
I would say that my graph went from -10 to 30, because that's what my graph is doing. And my graph is going from -10 up to 80. And it looks roughly like this.
It's like my y. No, my y is 30. No, my x is 30. What am I doing with my y?
Does this graph match what we would expect? Well, it looks quadratic, which it was an x squared, so that fits. It's upside down, that's due to the negative sign. So I think everything seems to be falling into place where I'd expect it to. What's that y-intercept at?
0 and 12.
Yeah, 12, right? Because the last number on there is 12. So I'll just need a few of you guys to help out with those x-intercepts and the maximum point way up there at the top, wherever it is. I'll do the maximum point if someone else wants to work on the zeros, maybe. So the maximum tells me it's at, okay, so look at this one here. This one says it's at 6.499999. If you guys just want to take a quick peek at what my calculator shows you here. 6.49 repeating. 6.5, yeah. We'll call it 6.5. And 5425. Anybody calculate a zero?
I got negative 0.9.
Negative 0.9.
And 13.
13?
I got 0.9.
Are those like right on the dot?
13.86.
Okay. So like those were rounded numbers that you had to round for me.
So I accept.
So 13.9 basically?
Yeah.
Okay. Okay. Okay, let's talk through some of the other properties. So I have a few more for your list then. Let's do domain and range first. So domain, x element of the reals, range. What's the range of this graph? Yeah, y is less than 54 point. It's actually 25, by the way. 54.25. 0.25. Okay, a few other things I might want you to get asked about. What's the degree? The degree is 2, which makes it even, just in case you're getting asked that question. In terms of end behavior, I don't know how you want to write end behavior, but like it starts and ends in the same quadrant. So maybe you could say like your end behavior is like on the same side. Because if it was an odd, it would be across the grid. It would be on opposite sides. So. Make sense? Okay. Okay, I'm almost done here. Then we can be done with a set of notes, I think. Here's an example of something they might give you on the diploma. They might give you 4 equations and 4 graphs, and they might ask you to match the equation to the graph. Which, I mean, one of the ways you can do it is type all 4 equations into your calculator and see which one fits. That being said, I'd hope that you could just look at the graphs and have some rough idea of it. Okay. Another thing they've been really tricky on, by the way, in the math 30-1 diploma is when they give you the equation, they do this. They say negative 2x squared minus ax.
Yeah.
And then you can't really type it in because you don't know what a happens to be. Does that make sense? Or they might say ax to the 3 plus bx plus 8. And so you really can't type the equation in. So you have to have some knowledge of what it does based on looking at the equation. So let's try matching them. Let's do this one down here first. Minus 3x minus 7 is the only linear graph on here, right? So the linear one should be that one. That one looks linear. Does it have a negative slope to it? Yeah, looks like it's fitting pretty well. Negative 7 is the y-intercept. Life is good. Let's look at the quadratic one. Here's a quadratic graph.
It's the one on the top.
It's the one on the top because we know it's upside down. Does that make sense? The negative makes it upside down. Where's the 1 to the power of 3?
That's the one on the bottom.
Yeah, it's a positive. Now there's a little flippy section right up here at the top of the graph, but that fits. This last one here, it's probably very difficult to see, but I imagine that somewhere in that little section down there, there's probably a little flippy wave happening down there, which is why it turns to the power of 4. We just can't see it because we're zoomed out too far. Does that make sense? So it's a power of 4 because it's doing like a little wave section if we could zoom in close enough to see it. So there, we got it matched. Does that make sense? Cool. Okay, what's left here? You know what? This one's basically the exact same concept. You just need to match them. Why don't I leave that for you guys for later? Let me go to my summary slide, and then I'll call it a day. So here's what I need you guys to know. Here are some of the key words. I think we've used most of these so far. X-intercepts and Y-intercepts. End behavior, I mean, does it go across the grid? Or do they both start into the same side? Domain and range, we've used before. I didn't use this word already in class today, so I should talk about it now. The word turning points. Turning points are exactly like you think the word would be. It's where the graph turns around. So, for example, on this graph right here, this is a turning point. This is a turning point. Does that make sense? Normally on a quadratic, we give the turning point a special name. We call it a vertex. But just in general, we call them turning points on different ones because here's where they turn around. Okay. Now, remember how a cubic could do this and actually have like a bit of a flippy in the middle here? It is also possible that it just does that. Kind of has a little bit of a bend to it. This one right here does not actually have a turning point, whereas this one right here does have turning points. Do you guys know how you'd find those?
You just go like minimum and maximum.
Exactly, yeah. This one's a maximum, and this one's a minimum. Okay, so I never used that phrase before, but that's what you might call it. Do you guys remember what standard form means? Yeah, the way it's supposed to be written. So if you write it as like 3x squared plus 7x plus 1, the reason why standard form is so useful is it tells you what the leading coefficient and the last term happen to be, the constant term happen to be. So standard form is just the way you write it. Let me show you an example, though, of something not in standard form, just so you're clear. Is this equation right here in standard form? No. To get it into standard form, you could do a whole bunch of foiling, which maybe isn't all that enjoyable, but you might be asked to put something into standard form. And what else do I got here? Oh, leading coefficients, of course. So here's what hopefully we accomplished today. You guys should now be able to roughly tell me what any polynomial looks like. I mean, to the power of 5 or 6 for sure, but if I asked you to draw me a polynomial to the power of 10, hopefully you could say, okay, well, to the power of 10 means that it should, like, say, start and end up here. So, like, 1, 2, 3, 4. So that would be quadratic. That would be to the power of 2, to the power of 4, to the power of 6, to the power of 8, to the power of 10. This could be to the power of 10. Something like that. Does that make sense? So, okay, homework time again. You didn't do this last time. Okay. In the journals I gave you guys, the sheet on solving polynomial functions worksheet. I mean, you got 20 minutes today. Can I say try to add 4 more to your collection? And then after you've added 4 more, if you want to take off, feel free. If you want to do it for homework, that's fine. But some of you didn't do it for homework last time, so shame on you. Okay. But other than that, I'm kind of done for the day. So, but why don't we try 4 more, okay? On Friday, by the way, I do want to collect these journals, and I'm going to mark probably your best 10 again. So make sure you actually have some of these done. One more thought. Don't just do linear and quadratic. Try to pick some things out of the power of 4 or 5. Try some challenges. Sound good?
Well, it's like,
Good job. But that's not recycling.
recycling.
No. All right. If you guys want to take off, sign the board. See you later then.